Hello, let's review one paper, which is artificial intelligence based novel design chart for doubly reinforced concrete beams, published by Journal of Asian Architecture and Building Engineering, and the author includes myself and my students at Kyung universities. This paper proposes a artificial neural networks to design doubly reinforced concrete beams, especially ductile, doubly reinforced concrete beam designs. And the design chart were made using artificial intelligence, which is artificial neural network, in particular in this paper. The methodologies are very innovative, we think, and let me go over briefly how we did it to come up with a design chart, especially very new type of design chart for designing ductile reinforced concrete beams which has a double reinforcement for the section top and bottom for compression and tension joints. Here, this is a doubly reinforced concrete beam sections and side views, and we have a both rebars here and rebars here, whereas the B is width of the beam section, and D is the effective depth of the beam, and H is gross depth of the beam as well. We have here L, which is length of the beam, span length, and we have some loading Q, as you see over there for the designs. And here also we have a strain distributions from a neutral axis, where we have strain from concrete sections for compression zone, and we have a tensile strain from rebars, as you see right there. And we assume a fixed boundary conditions, so that the design is for a fixed reinforced concrete beam, as you see here. Take a look at how we can use artificial neural networks to perform a reverse design of reinforced concrete beams. Here we have a conventional designs based on forward calculations, where we need a appropriate number of input parameters on an input side to calculate output parameters on an output side. The blue circle represents input parameters, and red box also represents output parameters. Usually the conventional designs based on forward calculations is performed using a structural mechanics. All the structural softwares can be used to perform a conventional designs, and they are based on forward calculations. Whereas we have here the reverse design that we need to take a look at using artificial neural networks. For example, the parameters you see here, the phi-mn and mu and mu phi, which represents the design moment strength and the affected moment and curvature ductility, now are pre-assigned reversely on an input side in order for us to control these parameters as a design targets. Whereas some of the parameters from input should move to output side. In this case, we moved HD, rho T, rho C to the output side. So that some of the input and output parameters are exchanged to pre-assigned variables of interest to prescribe the values. For example, we can prescribe the design moments, and mu actually is equal to design moment, when this happens, then we have situation where the safety factor is equal to 1, which is very unusual that you can achieve for conventional designs. And then we can also prescribe a ductility of curvature, and these parameters are used to be calculated on an upper side, as you see over there, here phi mn here, and you have a ductility is also here for the calculations of conventional designs. But now these are are placed and reversely pre-assigned on an input side in reverse designs, which is very innovative, and it'll be very challenging for us to perform this type of analysis using conventional Ford calculations. And we define this reversely pre-assigned on an input side as a reverse input. Okay, so in step one we have placed the reverse input parameters, which is shown here on an input side. They are the actually design targets, so we can prescribe a special value for these targets in order to control or govern the design, govern the beam design, whereas we have to move some of the parameters from input to output. As you see here, in this case we have H, D, rho T, rho C be placed on an output side. We call these are reverse output parameters, whereas we call these reverse input parameters, so that by training artificial neural networks we can predict these values based on these new input parameters, including reverse input parameters. I'll explain in separate clip that how to train and formulates to predict reverse output parameters from the input parameters, including reverse input parameters. And that's a very simple if you formulate a artificial neural networks. And then in step two is making a Ford calculations where you can use the reverse output parameters that were calculated in step 1 as input parameters on an input side for step 2, and you calculate outputs. This is regular conventional design based on Ford calculations, and you can recall this diagram, and here you have a regular conventional input parameters and you calculate conventional output parameters. Now you have all the parameters are in here, including reverse output parameters, which are H, D, rho T, rho C. So if you use this using any type of software, can do this calculations, because this is a regular conventional designs, and you will be able to come up with the regular output parameters, including this, which were reversely pre-assigned on an input side in step 1. However, you don't need these values actually, because these values here, these three reverse input parameters were pre-assigned here. Well, pre-assigned here is a design target. So these are the design targets, but you still calculate here in step 2 as a for the calculations, so that we have two values. One we had assigned as a design targets for step 1. So let's summarize here. See, step 1 we had a m phi mn m nu u phi as a design targets, and these were reversely pre-assigned on input side. And then step 2, so this is a reverse network, and step 2 you can use any software, any structural software, because they are now for the calculations, and you calculate phi mn mu ductility, covered ductility one more time. So we have a pre-assigned value. Pre-assigned, you mean you just assign them as engineers decide depending on their interest of designs, and now step 2 you calculate it, so that you can compare these two values. You can compare these two values. One was pre-assigned as a target, design target, and the other values are calculated in step 2 based on any software, Ford based software, and you can verify. Now you are verifying whether your reverse network is doing and calculating reverse parameters accurately or not. If these values are not accurately compared or correctly compared, then you have to go and redo all the trainings and setting up a neural networks and whatever you need to do to fix these differences. However, if you have a similar values or with the little differences between, then you have succeeded perform a reverse design of reinforced concrete beams. And this is very simple, 2 steps to calculate the design parameters based on reversely placed input parameters. So let me summarize it here. This step 1, we have a reverse networks where we're going to put reverse input parameters on an input side as a design targets to come up with a reverse output parameters. But these reverse output parameters are used to be placed on an input side for regular calculations, as I emphasized a couple of times. And after we get HD, rho RT, rho RC, then these parameters are used as input parameters in step 2, which is for the calculations. Once you have all this HD, rho RT, rho RC in input side with the other regular input parameters, then now you are having a conventional for the design for step 2. So you go and calculate the outputs. The output will include these 3 reverse input parameters which were pre-assigned on an input side for step 1. So you can use any regular software to do this, so that you have here extra values. Extra values, I mean that you have these values already been pre-assigned as a design targets. So we have design targets as well. Design targets which were pre-assigned, so you can compare these values to conclude and to verify your back substitution method. So we call that back substitution method because the reason I call that is you just calculate this reverse output parameters in step 1, which is reverse network, and substitute back into the step 2, which is based on fold calculations, to come up with a design parameters, including the parameters that were pre-assigned reversely in step 1 based on reverse network. And the back substitution method can be verified. When you verify, these differences are small and negligible. This is an example of reverse design chart that I'll be explain how to derive in next clip. Just simply demonstrate how we can come up with a reverse design chart, and to show that how you use reverse artificial networks. And this is very convenient reverse design chart, because you can come up with any pre-assigned ductility, curvature ductilities. For example, if you want to go a 2.3 right there of curvature ductility, then you go all the way and hit the curve, and you go left to calculate rho RT, and you go right to calculate rho RC. Of course, this chart is prepared for each the vector moment or design moment, because they are same. A situation where we have a safety factor of 1, which is very challenging to achieve using conventional designs. And also this sequence of calculating or come up with a rho RT and rho RC, starting with a pre-assigned reverse parameter, this is very difficult or challenging using conventional designs here. And we have a bunch of lines over there. The half of them is prepared for rho RT, and half of them prepared for rho RC. And the moment ranges were covered from 1000 kilonewton meter to 5000, same for both rho RT and rho RC. So that we can go, say we're going to start 4.5 of curvature ductility, and you go here, for example, and this represents a rho RC for 3000. So you go here, then this value is rho RC when the moment were for 3000s. And for example, if you go here and this is solid line, yellow solid line goes here, and this value represents then this yellow solid line, the rho RT, which is a tensile lever ratio for 4000 moment, vector moment, or PMN. They are same because we have a safety factor of 1. And let me give you one more example here. Let's go say 3.5 and red dotted line, and you go left. So we have to go left if you hit the dotted line to get a rho RC for 3000s, right? 3000s here. And if you hit all the way to blue one, this one, you go left. Solid line, you go left to get the from legend solid line for blue. It's this 5000, right? So this is very easy to use this curve, the reverse design charts, and I'll show you how to create this design chart from the reverse neural networks we just took a look at in this clip. This is very simple process to create design chart, which is based on reversed input parameters, but they are very convenient to use because we can control now the ductility, curvature ductility in design, and we can also create a chart, start with a VMN, maybe whatever design targets you may need to control your designs of reinforced concrete beams.